Chemical vapor deposition is parent to a family of processes whereby a solid material is deposited from a vapor by a chemical reaction occurring on or in the vicinity of a normally heated substrate surface. It is used to deposit high-quality, high-performance solid films. The deposition usually occurs through a continuous process, where the deposition rate is influenced by various parameters like temperature, pressure, and gas concentration. CVD encompasses a wide range of techniques, each with its unique characteristics and applications. Based on operating pressure, CVD processes can be divided into high vacuum, low pressure, atmospheric, and high pressure CVD. Or based on physical characteristics of the vapor, or the type of substrate heating. Special types include the plasma-enhanced CVD, atomic layer deposition, or metal-organic CVD. In this lecture, we will only discuss low-pressure CVD and plasma-enhanced CVD. Low-pressure chemical vapor deposition is a variation of the standard CVD process. Depositions take place in a horizontal tube furnace that operates at reduced pressures, typically between 0.01 and 1 torr. Heat is used to initiate the chemical reaction at the surface, which forms the deposited solid film. The process temperature is usually between 425 to 900 degrees. The low pressure reduces unwanted gas phase reactions and ensures the uniformity across the substrate. Plasma-enhanced chemical vapor deposition is another variation of CVD. Depositions are done in a process chamber at low pressures. Process temperatures are considerably lower than for LPCVD, between 200 and 400 degrees. In plasma-enhanced CVD, plasma is used to provide the energy for generating the reactive species. Regardless of the CVD type, the overall reaction mechanism is the same. In a vacuum chamber, gas species react on a heated sample surface and produces a solid phase film. The overall reaction of most CVD processes consists of 4 steps. The substrate is loaded into the furnace or process chamber and heated up, either by heating the entire chamber or by solely heating the substrate. Then one or more process gases are introduced. They react in gas phase, forming the reactive species and some byproducts. If several gases are pumped into the chamber, they will react in gas phase, forming the reactive species and some byproducts. The reactive species diffuse and absorb onto the sample surface. Adsorbed molecules migrate across the surface to find suitable growth sites. A chemical reactions occurs between adsorbed molecules and the substrate, or among adsorbed molecules, leading to film formation and volatile byproducts of the chemical reaction. Please note that the deposition rate is limited by the surface reaction and not the arrival of reactive species on the sample surface. In the last step, byproducts are pumped out of the system. The deposition is a continuous process. There is a continuous flow of gases into the chamber. Simultaneously, byproducts and some gases are pumped out of the chamber. The deposited film grows until the introduction of new reactive species stops. The SEM image shows an example for a thin layer of silicon nitride deposited onto high aspect ratio trenches in silicon by LPCVD. CVD is a versatile technique with a wide range of applications across various industries. Here are some of the primary areas. Structural layers in the semiconductor industry encompass a wide range of components, including silicon-on insulator wafers, membranes, free-hanging cantilevers, or thin films utilized in transistors and integrated circuits. Furthermore, CVD can be used to deposit materials for optical devices such as waveguides and antireflective coatings. Functional layers like oxidation and etch masks, sacrificial layers, and insulating layers are essential to the fabrication process. For example, silicon nitride can be used as etch mask for long etches in potassium hydroxide. The etch rate for silicon nitride is with less than 1 angstrom per minute considerably lower than the etch rate for silicon at 1.3 micrometer per minute. CVD deposited layers can also be used for protective coatings or for decorative purposes.
Let's have a closer look at the process details for low-pressure vapor deposition. Low-pressure chemical vapor deposition at DTU Nanolab is done in furnaces. Same as in thermal oxidation furnaces, the furnace tube is made of quartz as it is a very clean materials and can withstand very high temperatures. More on that matter in the thermal oxidation lecture. The inlet for gases are placed close to the door. Mass flow controllers control the gas flows. Nitrogen is used as purge gas. LPCVD processes take place under vacuum, pump, valve, and a pressure sensor controls the overall pressure in the furnace and ensure that possibly toxic gases are pumping out and the chamber is purged before opening. A cantilever is mounted on the door on which wafers in a quartz boat are placed. The cantilever is made of silicon carbide or silicon carbide covered with quartz tubes. The furnace is heated by either 3 heating elements for 4 inches furnaces and 5 elements for 6 inches furnaces. The heating elements are coils wrapped around the furnace tube. They are placed in the middle part of the furnace tube. Therefore, only a limited area in the center of the furnace will have a uniform and stable temperature. Wafers should be placed here. For most furnaces available at DTU Nanolab, an arrow marked on the metal beam below the cantilever indicates the center position for the quartz boat. One exception is the E-stack where quartz with dummy wafers are always present and quartz boats for substrate wafers are placed in between. This will be explained in detail during the training session. Even though the process itself is relatively simple, the practical implementation is a bit more complicated than the oxidation process, mostly due to the presence of toxic and flammable gases in combination with high temperature during the deposition process. LPCVD furnaces are always running a standard process before opening of the furnace, ensuring cleanliness of the furnace. After purging with nitrogen and venting, the door opens and samples can be loaded into the furnace. After closing the door again, the furnace will pump down and perform a leak test to ensure no leakage of toxic gases can occur. The actual deposition process includes a second shorter leak test before the deposition is started and the chamber is heated up to the set temperature. Once the set temperature is reached, gases are introduced into the chamber and the deposition takes place. After the deposition, the furnace is purged with nitrogen for an extended period of time to remove all toxic process gases while the furnace cools down to standby temperature. Once the furnace has cooled down to standby temperature, wafers can be unloaded using the standby recipe. After closing, the chamber is set into an idle state using a standby recipe that includes another leak test and leaves the furnace under vacuum with a nitrogen flow. Like most thin film methods, LPCVD films are deposited, not grown. They form layer on layer. That also means that contaminations on the surface are encapsulated and remain close to the substrate surface. Contaminations on the surface can also locally prevent the deposition entirely and create pinholes. Those contaminations can be present on the substrate before loading into the furnace, but they can also arise from particles inside the furnace. Same as in other furnace processes, the deposition happens on all accessible surfaces including the wafer front and back side. Several wafers can be coated in a batch process with uniform thickness and good step coverage of structured areas. The LPCVD process offers commonly a very high reproducibility and easy control of film composition and stoichiometry. But the process has also some drawbacks. With 550 to 850 degrees, it operates at a high temperatures which together with often toxic and or flammable gases is not a safe combination. For that matter, LPCVD furnaces at DTU Nanolab can only be used within working hours, Monday to Friday from 8 a.m. to 4 p.m. Furthermore, LPCVD processes have also a low deposition rate of 0.5 to 2 angstrom per second. At DTU Nanolab, 3 materials can be deposited using LPCVD furnaces: silicon nitride, silicon, and TiO silicon oxide, which are frequently used for various applications. In the following slides, the deposition of each material and its properties will be explained in more detail. Silicon nitride is deposited by LPCVD using dichlorsilane and ammonia. Hydrochloric acid and hydrogen are formed as byproducts in the gas phase. The byproducts will mostly be pump out, though hydrogen can be incorporated in the deposited film. The SEM image shows an example of a cross-section with silicon nitride deposited on a silicon wafer. At temperatures below 130 degrees, another unwanted byproduct, ammonium chloride, can be formed by condensation. Those can sometimes be observed at the furnace door or in pump lines as white particles. Ammonium chloride can irritate the respiratory system as well as eyes and skin and should be handled with some caution. Please contact a staff member from DTU Nanolab if you observe white particles. Stress is an important factor when talking about silicon nitride films. Together with the refractive index, it can be adjusted by changing the ratio between the deposition gases and slightly by adjusting the temperature and the pressure. If the glass flow ratio between dichlorsilane and ammonia is 1:4, stoichiometric nitride, C3N4, is deposited. That means 3 silicon atoms and 4 nitrogen atoms form one silicon nitride molecule. Stoichiometric nitride is very dense and therefore exhibits high quality, but also high tensile stress, in contrast to thermal oxide, which displays compressive stress. In the nitride furnace at DTU Nanolab, the tensile stress is about 1150 MPa. For inverted gas flow ratios of 4:1, silicon-rich nitride is deposited. It is also called low-stress nitride as it has a much lower stress than the stoichiometric nitride. This type of nitride is often used for the fabrication of nitride membranes to avoid stress and cracking. Be aware that hydrogen is incorporated in low-stress nitride films, which reduces the density of the film. The risk for the formation of unwanted ammonium chloride increases with increasing amount of dichlorsilane compared to ammonia. Even though it would be possible to achieve zero-stress nitride films by increase the amount of dichlorsilane, it is mostly not allowed at DTU Nanolab to reduce the contamination of furnace chamber and pump lines. In fact, furnace B2 LPCVD nitride, 4, is solely dedicated for the deposition of stoichiometric nitride where low particle density often is a requirement. Standard recipes available at DTU Nanolab offer a balanced compromise between the stress in the deposited nitride film and the appearance of particles. Please be aware that the stoichiometry in the nitride film, meaning the proportion of components, can vary across the wafer and within the nitride film layer. LPCVD silicon is deposited by the thermal decomposition of silane to silicon and hydrogen. Even though it is possible, the amount of hydrogen incorporation into the deposited silicon film is typically low compared to other deposition techniques like plasma-enhanced chemical vapor deposition. The SEM image shows an example of a cross-section with polycrystalline LPCVD silicon deposited onto a silicon wafer with a thin silicon oxide layer in between. At DTU Nanolab we require users to include a test wafer for all furnace processes to measure the thickness of the deposited layer. For obvious reasons, it is important to use a test wafer with a known oxide layer on top to be able to measure the thickness of the deposited LPCVD silicon layer. DTU Nanolab supplies those test wafers. The crystal structure and the deposition rate for LPCVD deposited silicon depends on the deposition temperature. For temperatures below 600 degrees, amorphous silicon is deposited with a relatively low deposition rate of 2 to 4 nanometers per minute. If the temperature is increased to between 600 and 650 degrees, polycrystalline silicon with a preferred grain orientation of 1 to 10 is deposited. Due to the increased surface mobility, silicon atoms can move to low-energy, crystalline positions. The deposition rate increases to 8 to 10 nanometers per minute. At temperature above 650 degrees, still polycrystalline silicon is deposited, though with a preferred grain orientation of 100. This is not a standard process at DTU Nanolab. Polycrystalline silicon has a columnar structure. It consists of small grains of a single crystalline silicon separated by grain boundaries. These grains will grow from the wafer surface and upwards. The grain size of polysilicon significantly impacts its electrical properties and device performance. The deposition temperature and post-deposition annealing can significantly influence the grain size. Higher deposition temperatures as well as annealing after deposition can significantly increase the grain size. So, annealing of polycrystalline silicon will increase the grain size and reduce the stress. Annealing of amorphous silicon at temperatures between 600 to 1100 degrees will turn it into polycrystalline silicon. During this process, the silicon atoms gain enough energy to overcome the energy barriers preventing their movement. As a result, they rearrange themselves into a crystalline structure, forming polycrystalline silicon. Again, the higher the annealing temperature, the larger the resulting grain size and the lower the film stress. Please note that polycrystalline silicon at DTU Nanolab is often referred to as polysilicon. In the LPCVD furnace, the deposited silicon can be in situ doped with either boron or phosphorus. Adding D-borane or borane chloride to the silane gas causes a small increase in the deposition rate because D-borane forms borane radicals that catalyze the gas phase reactions and increase the deposition rate. In contrast, adding phosphine or arsine to the silane gas causes a rapid reduction in the deposition rate, up to 10 times slower. Phosphine or arsine are strongly adsorbed onto the silicon substrate surface, thereby inhibiting the dissociative chemisorption of silane. The addition of phosphorus to the silane gas will also reduce the temperature required for inducing crystal growth, turning deposited silicon at lower temperatures into polycrystalline silicone that in an undoped process. At DTU Nanolab, phosphorus doping can only be done with phosphine in the B4 furnace. Doping decreases the resistivity of the deposited silicon, thus increasing its conductivity. Hereby, doped polycrystalline silicone has a much higher resistivity than doped single-crystal silicon. In polysilicon, dopants can segregate along grain boundaries, leaving only few dopant atoms within the grains. TiOS oxide is called after the chemical that is used for the deposition process. TiOS stands for tetraethyl orthosilicate, which is a liquid, not a gas. For the deposition, the TiOS is heated in a bubbler to 75 degrees, vaporized and then introduced into the furnace. Silicon oxide is then formed by thermal decomposition of the TiOS on the sample surface. Water and ethylene are produced as byproducts, where the latter sometimes decomposes to carbon. That carbon can be incorporated into the deposited silicon oxide film. The crystal structure of the TiOS oxide is amorphous. It can be annealed at around 1000 degrees, which increases the film density and thereby decrease the thickness. The film quality will become close to thermal oxide. TiOS oxide is deposited, not grown. It is often used where a silicon oxide film is required on a non-silicon surface. Thermal oxide will only grow on existing silicon surfaces, as explained in more detail in the thermal oxide lecture. The TiOS deposition process has a very good step coverage, as the TiOS molecules have a high mobility at the sample surface. The stress is with 100 to 300 megapascal, slightly compressive, like amorphous oxide. Carbon contamination can be integrated into the film during film deposition. Let's round up the lecture with a presentation of LPCVD furnaces available at DTU Nanolab. As explained previously, only the loading area is accessible in the common area, while the actual furnace with pumps and other equipment is located in the service area. The B-stack furnaces. There are only 3 furnaces available, and there is no furnace called B1. Furnace B2 allows the deposition of stoichiometric nitride on batches of 15 4-inch wafers simultaneously. Furnace B3 allows the deposition of TiOS oxide on batches of 15 4-inch wafers simultaneously. Furnace B4 allows the deposition of amorphous and polysilicon on batches of 34-inch wafers simultaneously. It can also be used to dope the LPCVD silicon with boron or phosphorus during deposition. The E-stack furnaces. Furnace E1 is not an LPCVD furnace. It's used for thermal oxidation of silicon. Furnace E2 allows the deposition of amorphous and polysilicon on batches of 25 4 or 6-inch wafers simultaneously. It also allows doping with boron, but a gas injector needs to be mounted. Furnace E3 allows the deposition of silicon-rich, or low-stress nitride, on batches of 25 4 or 6-inch wafers simultaneously. It can also be used for deposition of stoichiometric nitride, though only on batches of 25 6-inch wafers. Please note that at DTU Nanolab, LPCVD depositions are only allowed on working days between 8 a.m. and 4 p.m. Finally, here's an overview over all LPCVD furnaces that can be used to deposit nitride, silicon and TiOS oxide. If you have any questions regarding LPCVD deposition or the furnaces available at DTU Nanolab, you are welcome to contact us. The furnace responsible persons are Panil and Patama on the process side, and Fleming on the technical service side.
Now, let's have a closer look at the process details for plasma-enhanced chemical vapor deposition. Plasma-enhanced chemical vapor deposition uses plasma to add energy to the reaction that is required to form the reactive species. The temperature can therefore be kept considerably lower than for LPCVD. That enables deposition on temperature-sensitive samples, such as metals or 3,5 materials. Apart from that, the same materials can be deposited using PECVD like using LPCVD, though the molecular composition of the materials may vary. At DTU Nanolab, following materials can be deposited by PECVD: silicon nitride, silicon oxide, silicon oxynitride, amorphous silicon, and borophosphosilicate glass. These can also be doped in situ with boron and/or phosphorus. PECVD allows for far more flexibility in tuning processes to create, for example, silicon oxynitrides of different stoichiometry than LPCVD does. Applications for PECVD films are mostly the same as for LPCVD films, for example for optical devices, making insulating layers, membranes, or cantilevers. But they can also act as etching masks or protective layers. For example, PECVD films are often used for waveguide. The image shows the basic process steps for making waveguides. The substrate is coated with a lower cladding. On top, a waveguide core is deposited. After etching the waveguide core into lines, they are covered with another cladding layer. For the functionality of guiding light through waveguides, the core and the cladding material must have different refractive indices to guide the light along the lines. This is an overview of a PECVD system. The processing chamber consists of two parallel plates that works as two electrodes. The bottom electrode, where the substrate is positioned, is grounded, and the top electrode is connected to a power generator through an impedance network. The power generator generates an AC potential in the radio frequency range of 13.56 MHz, or at lower frequency, at 380 kHz. Process gases are pumped into the chamber through the top electrode, which has a lot of holes like a shower head. The flow rate is controlled by mass flow controllers, or MFC. The pressure in the chamber is measured with the pressure gauge and controlled by the pressure controller. Plasma consists of positively charged ions and negatively charged electrons. In the plasma, different type of collisions taking place. Here we will only explain the two most important collision types for the PECVD process. More details about plasma and its properties are explained in the PVD lecture. The first is called dissociation. When a free electron collides with a molecule, that molecule splits up into two or more reactive components, called radicals. In the process, no additional electrons are released, which help in maintaining the plasma. The second is called ionization. When a free electron collides with a free atom or free molecule, it loses an electron and becomes a positively charged ion, called striking ions. The function of the reactive radicals is quite straightforward. They are reacting on the sample surface to form the film. They can also react with other radicals in the gas phase. The function of striking ions is not that simple. Striking ions bombard the sample surface and thereby transfer energy to the sample surface and create some defects. These surface defects are also called the active sites. The ion bombardment also assists in densifying the deposited film. Unfortunately, they can also incorporate defects in underlying layers. This is usually not a problem, unless thin layers of 3,5 materials are deposited. Well, the deposition process starts with generating the plasma by applying an alternating voltage. The voltage accelerates electrons that collide with neutral gas species, which create ions and neutral radicals. These radicals are very reactive and partially act as the precursors for the deposition. There are two power generators connected to the system. One running an AC potential at 13.56 MHz, and the other running at 380 kHz. So, how does the frequency affect the deposition? At 13.56 MHz, the switching of the polarity of the electrode is too fast for the ions to follow, as they are too heavy. They cannot bombard the sample with significant energy, so the ion bombardment energy is low. It is, however, not zero, since the plasma potential will have a small positive value due to electrons leaving the plasma. This small difference is enough to accelerate positive ions towards the ground bottom electrode. There will be less ion implantation into the film and therefore less damage of underlaying layers. At 380 kHz, the switching is slow enough for the ions to follow. They will flow towards the bottom electrode, sputter the sample with much higher energy. The film gets denser, which leads to lower wet etch rates, and for example more compressive silicon nitride films. A colleague at DTU Nanotech, Thomas Pedersen, has done some experimenting regarding deposition of low-stress silicon nitride using the PECVD. By switching between the high-frequency generator and the low-frequency generator, low-stress silicon nitride film can be obtained. He found that the stress level can be very well controlled. If the deposition is done at low frequency for 60% of the time and high frequency for 40% of the time, silicon nitride can be deposited with zero stress. While the frequency clearly has a large effect on the film deposition, the influence of gas flow ratio, pressure, power, and temperature should be noted as well. Same as for the LPCVD process, the gas flow ratio has a strong influence on the stoichiometry of the deposited films. The lower the chamber pressure, the longer the mean free path of the atoms and molecules. That leads to higher ion bombardment energy, which will improve the film quality by informing denser films. It also results in lower compressive stress in silicon oxide films. However, a too low pressure will turn the deposition into a PVD-like deposition with more defects. Furthermore, the higher the power, the larger the deposition rate. It also results in higher ion energy. If the ion bombardment per deposited molecule increases, the film density and therefore film quality increases too, and opposite. Finally, the temperature affects the film quality, and higher temperatures result in high film quality. At DTU Nanolab, we have limited the temperature to 300 degrees. As previously mentioned, following materials can be deposited at DTU Nanolab: silicon oxide, silicon nitride, silicon oxynitride, and amorphous silicon. These can also be doped in situ with boron and/or phosphorus. Please note that the layers made by PECVD are not stoichiometric, and they all commonly contain some amount of hydrogen. That makes the films less dense and reduces the resistivity to many chemicals. The molecular composition of deposited films depends on the various parameters, though mostly the gas flow ratios. Annealing at elevated temperature improves the coverage of corner and holes and thereby the quality of the films. The left SEM image shows the cross-section of lines. They have been covered with BPSG oxide. As the BSPG oxide is heated above 1000 degrees, it starts to soften and finally floats. The layer smoothens out and corners become rounded, as shown on the right SEM image. This can be used, for instance, for optical waveguides to cover the structures with a smooth layer. At DTU Nanolab, two PECVD are available: PECVD3 and PECVD4. PECVD1 and 2 has been decommissioned some time ago. PECVD3 is the dirty PECVD. Here we allow metals on the substrates up to a coverage of 4 square centimeters per run. This allows coverage of metal vias or similar. PECVD4 is dedicated to clean silicon processing and clean 3,5 material processing. Silicon and the 3,5 materials are processed on top of dedicated carriers to avoid cross-contamination between the two material types. The instrument is handled from the cleanroom area where the load lock and the computer are located. The actual process chamber, pump, chiller and other equipment are placed in the service area. If you have any questions regarding PECVD tools, you are welcome to contact us. The responsible persons are Berit on the process side, and Roy on the technical service side. The SEM image shows two profile images of high aspect ratio trenches in silicon. They have been covered with silicon nitride and silicon oxide from the LPVCD furnace and the PECVD, respectively. The LPCVD process has covered the trenches very nicely with uniform thickness in the bottom and the top. The PECVD process has not covered the trenches as well. In fact, there is almost no deposition at the bottom of the trenches. Even the thickness at the side wall is generally thinning towards the bottom. For low aspect ratio structures, the step coverage can be almost as good for PECVD as it is for LPCVD. Let's finalize this lecture about LPCVD and PECVD with an overview about the two processes. We will not go into detail, but you can use the slide to look up information about both processes and the available tools. This information can also be found on Lab Advisor. This material has been compiled as part of DTU Nanolab's initiative to provide our users with a deeper understanding of the theoretical principles behind our cleanroom equipment.